Welcome back friends. Again we are going to discuss about phase detectors. The analog multiplier as a phase detector. A cos omega t we are given to the detector. Here it is mixing with B cos omega phi plus phi. Then the output will be like that. In PLL that have sine waves inputs and sine wave VCOs. The most commonly used phase detector is the multiplier in PLL that have sine wave inputs and sine wave VCOs. The most commonly used phase detector is the multiplier. For an ideal multiplier, it isn't too difficult to derive the input-output relationship. Using some trigonometrical identities, we find that the output of the multiplier may be expressed as like that. AB cos omega t plus phi is equal to AB by 2 of cos phi minus cos 2 omega t plus phi. Note that the output of the multiplier consists of a DC term and a double frequency term. For phase detector operation, we are interested only in the DC term. Hence, the average output of the phase detector is AB cos omega t plus phi is equal to AB by 2 into cos phi. Analog multiplier as a phase detector. We see that the phase detector gain constant is a function of the phase angle and is given by Kd is equal to d by d phi of V out is equal to minus AB by 2 of sin phi. If we plot the average output as a function of phase angle, we get something that looks roughly as shown in the given figure. Next. Notice that the output is periodic. Further note that the phase detector gain constant is 0 when the phase difference is 0 and is greatest when the input phase difference is 0. Hence, to maximize the useful phase detection range, the loop should be arranged to lock to a phase difference of 90 degrees. For this reason, a multiplier is often called a quadrature phase detector. When the loop is locked in quadrature, the phase detector has an incremental gain constant given by the following equation. A cos omega, here the commutating multiplier as a phase detector. So here the A cos omega t and B SGN of cos omega t plus phi both here multiplying with the one function. A cos omega t that is given B sin of cos omega t plus phi both are mixed and is given to AB cos omega t into SGN of cos omega t plus phi. In the previous section, we assumed that both inputs to the loop were sinusoidal. However, one or both of these inputs may be well approximated by a square wave in many cases of practical interest. Let us now modify our results to accommodate a single square wave input. In this case, we have the situation depicted in above figure where SGN is the signum function defined as signum of x is equal to 1, signum of x is equal to minus 1. If x is greater than 0, equal to 1. If x is lesser than 0, it is equal to minus 1. Now recall that a square wave of amplitude B has a fundamental component whose amplitude is 4b by 5. If we assume that we care about only the fundamental components of the square wave, then the average output of the multiplier is given B of out is equal to B of out is equal to 4 by 5 into AB by 2 into cos phi is equal to 2 pi AB cos phi cos phi. Next, the corresponding phase detector gain is similarly just 4 by pi times as long as in the purely sinusoidal case. That is kd of phi is equal to pi by 2 is equal to d by d phi v out at tends to phi is equal to pi by 2 is equal to minus 2ab by pi. Although the expressions for the phase detector output and gain are quite similar to those for the purely sinusoidal case, there is an important qualitative difference between these two detectors. Because the square wave consists of more than just the fundamental component, the loop can actually lock onto harmonics or subharmonics of the input frequency. Then the exclusive OR gate as a phase detector. If we now drive an analog multiplier with square waves on both inputs, we could analyze the situation by using the Fourier series for each of the inputs, multiplying them together and so forth. In this case also, the two square wave inputs produce the output shown in the figure below. As we change the input phase difference, the output takes the form of a square wave of varying duty cycle, of varying a duty cycle with a 50% duty cycle corresponds to a quadrature relationship between these points, relationship between the inputs. Here the model graph is like this. Here exclusive OR gate as a phase. Since the duty cycle is in fact proportional to the input phase difference, we can readily produce a plot of the average output as a function of the input phase difference. The phase detector constant is also a constant in this instance and is equal to kd is equal to 2 by pi into ab. Next, we see that within a scale factor, this phase detector has the same essential behavior as an analog multiplier with sinusoidal inputs, again interpreting phase errors relative to quadrature. Next, for the special case where the inputs and outputs are logic levels that will swing between ground and some supply voltage VDD. The phase detector output has an average value that behaves as graphed in figure. The corresponding phase detector gain is then kd is equal to VDD by phi. The characteristics of XOR or as quadrature phase detector as a quadrature phase detector. Loop filters and charge pumps. So loop filters and charge pumps.